Hi guys, today I'm gonna have a long review of the classical paper Conformer Convolution-augmented Transformer for speech recognition, which was published almost 2 years ago. But as time goes by, I personally get better understanding of the paper, and I found that I haven't reviewed the paper yet. So I think since I haven't done the transformer paper review, I'd better to add this conformer paper review, so to help you guys to use the conformer in speech recognition, because conformer model is currently a state-of-art encoder module for speech recognition. I think first of all, the key thing the conformer brings is that considering that transformer models are good at capturing content-based global interactions, and also the CNN only explore local features effectively. So these authors, they combine the transformers, they combine the self-attention with the CNN. That's their main innovation part, and it worked very well for the standard speech benchmark, which is LibriSpeech. And you can see that on the right side, you can see the conformer encoder model architecture. But you can see that they are still trying to work under the transformer architecture. So they remember the encoder, the decoder, and the cross attention between the decoder from the decoder to the encoder. Okay. The only thing they changed is the conformer block, or they introduced a new one. Remember, before the conformer block, they have something called a self-attention block, or transformer layers. Let me see if I can draw it here, okay? This is transformer look like? What does a transformer module look like? First of all, it has a feed forward module also. And I think it used the ResNet connection, of course. I'm sorry, I think in the beginning it uses the multi-head self-attention. And they leverage the ResNet connection. Yeah. And after this, they use a feed-forward module, which takes the multi-head self-attention module's output, and they follow the ResNet connection. Again, they might have a norm. Maybe I kind of forget. Maybe the layer norm, batch norm, whatever. But you can see this is transformer, the original transformer block in the encoder, but this is conformer. The biggest difference is that, first of all, they add another new feed-forward module at the very end, okay, and another one. And the second thing is that, which is more important, is the introduction of this convolutional module. Okay. And they actually didn't generate the idea from nowhere. it's from a ICLR or IC whatever conference. There's something called I think this whole architecture comes from something called the Macronet. Macronet. You can search this. This is exactly architecture people use. The Macronet author uses in their paper, but Macronet was tested on the machine translation. The authors didn't try on the speech recognition. Well, these authors say, okay, can this thing work for speech recognition? They give it a try. It worked so well. Okay. For those of you interested in the Macronet, I recommend you to read the reference, not the 14. Gotta have to search using my eye. Oh. It gotta be somewhere. Not this one. QANet. Search for activity. I don't know why this doesn't have Macron here. Anyhow, so let's look at the exact network architecture. I just now I give you the general architecture of the conformer encoder. It's done by introducing this conformer block, then stack up each conformer block by n times. So you eventually get a conformer encoder. While the spectral augmentation, convolutional subsampling, these type of things, this is exactly the same as a transformer. Multi-head self-attention. I think there's a fairly standard. Yeah, but the only new thing here is that they use these. They use the relative positional embedding, other than just positional embedding. This is not new either, because people have tried that relative pos could improve the performance. Okay. Why? I guess you could go to the paper and check out why, but my understanding is the when the transformer look at the context, the absolute position thing makes less sense compared to the relative positional embedding, because when you look at the current frame or current input, the one before it, the one next to it, it's the relative location, right? Relative position, relative context. It's not, say like this, okay? For instance, suppose at the sentence beginning I said I have a cat, but what if so you see, for the have, the cat is the position, the position of the cat. So have position says in the relative, suppose I use in the absolute position, okay, have is 0 is 1, and the cat is 3, right? So cat position is 3 due to position 1. But it could be that there's another sentence which is Bob found that I have a cat. So in this time, this is 0, 1, 2, 3, 4, 5, 6. Okay, so they have the position is 4, but cat position 6. But you think about the relatively or the correlation between the words and have and cat. In my personal opinion, under these two sentences, they're roughly the same, right? It's all about have cat. But in this case, using the position 1 and 3 and the 4 and 6 is which makes the model harder to learn, okay? Especially you don't encode have. You don't encode this, and you don't encode this. You encode the position, the absolute position, 3 and 6. So it's hard for a model to find out, okay, what's the relationship. But if you're using the relative position, the cat is +2, right? And this cat is also +2. So you see the information again and again, so intensify the learning. So your model could be learning better. Okay. Convolutional module. I think they say they first use, you can see this is a convolutional module. It's not just a 1 CNN. Okay, this is they actually there happen 3 CNNs out there, or 3 convolutional things happen there. First of all, it's a pointwise convolution and a gate linear unit. Gate linear unit, and it is followed by 1D depth convolution right there. So I want to mention that. So if you combine the pointwise convolution and the depth-wise convolution together, it's what? It's called search the word. It's called separable convolution. So what is the purpose of doing this? The purpose is to reduce the computational costs. Because I don't have time to go into details. All you have to remember that the model gets smaller compared to using a full convolution versus full convolution. This is faster when the model size is similar, is the same, faster. So say, or this one can support bigger model size, right? Because it calculates faster. As you know, that when the model is bigger, your model can take in more data, so your performance gets better. Okay. But I personally still haven't fully comprehend this. This extra pointwise convolution at the end. So I can understand if you combine these two. So if you can help me, just let me know. I can understand if you decompose or disengage the full convolution into these depth-wise convolution and the point-wise convolution to reduce the cost, or you break up the convolution into this and this, right? And also it can reduce the computational cost. But after you do this, then you add this extra point-wise convolution, or you do this and you add this point-wise convolution in the beginning. It seems that to me, my current understanding is that you still you're not contented with the full convolution. You want to do something extra, so you want to do another. That's my word, okay? Half convolution, something like this. So you can see that you actually increase your model size by doing this. For the gated linear unit, I don't think it's super sophisticated. You just have a gated activation. And they use a switch activation they claim that this is faster than ReLU. This is what it said, faster than ReLU. You can use ReLU for sure. Okay, another thing you want to pay attention to is they put activation after the batch norm. I think there's an interesting article on the Reddit, people arguing whether you should put activation before the batch norm or you should put the batch norm before the activation. I think I saw some results. It's actually, you put the activation before the batch norm, you can get better results on the ImageNet task. But this one, they use the batch norm first. Okay, we've done with the convolutional module, so we move on to the feed-forward module. I think the feed-forward module is also internally speaking, talk about the content of the feed-forward module. It's different than the feed-forward module people use in the transformer or standard transformer. As you can see, it's slightly sophisticated. Especially they use this switch activation. Yeah, but regarding layer norm and the linear layer, correct me if I'm wrong. I think transformer also use 2 linear layers. Okay. Yeah. But definitely this is different than the standard transformer. Okay. But this is easy to understand, right? So, okay, I will move on. And let's look at so we have done with the modules, okay? The convolution module, feed-forward module, and the multi-head attention module. So let's revisit the conformer block again. You see, or the Macronet. I hate this, but in case your math is good, let's look at the math. It's easy to understand, trust me. First of all, this is ResNet connection, right? But they use a half step. This is ResNet connection. And then this is also ResNet. Anything comes with this plus sign is the ResNet connection, okay? This is all ResNet. Everything is ResNet. And then they use the multi-head attention. So this is multi-head attention module. And this is a convolutional module. And finally, after but this is half step. This is a full step, right? Full step ResNet. This is also full step ResNet. And this is a half step ResNet. And then finally, they use a linear norm. Okay. Let's look at this again. Okay. So see, feed forward, multi-head attention, convolution module, feed forward, and layer norm. Because these have, so this is why this is like a Macron, right? In Macron, you have the top stuff is maybe a green band. Okay, the bottom is also a green band. 2 feed forward there. Okay, and you have the stuffing. The stuffing they use is the multi-head attention module plus the convolution module. I think I like the coloring. You see, they make the stuffing to be yellow and red. Okay, and they call that a sandwich style, but I think the same thing, right? Sandwich top and bottom are all bread. You know, the inside can be lettuce and tomato and ham, different layers of that. That makes sense to me too. Yeah. Oh, I finally got the original paper. It's at 18. Okay. Let's quickly move to the 18 and take a look at the 18. Yes. I do recommend you to read this one. I think this is a very, very good or important paper which inspired the author to come up with this paper. Okay. So we've done with the conformer block, okay? Yeah, we're done with the network architecture. So they use the transformer, they change the transformer's encoder, but regarding the decoder, they use the vanilla 2 layers of LSTM. And then regarding the cross attention between the encoder and decoder, it's the same as the standard transformer. I will skip the settings of the data and this type of tedious learning reach settings. You can always check it by yourself. But this is interesting. Even I don't quite understand what is a variational noise, but I will check that later word. Yeah, they have the model with and without language model. They tried it on the LibriSpeech. LibriSpeech is a standard benchmark of speech. They compared the 3 different sizes of their models. Small, medium, large. It's parameters, easy to understand. Okay, so let's look at their results. Okay. Make this greater so you can see it better. So the hybrid means the acoustic model plus language model plus phone language model. It's a hybrid model. So this is called hybrid. This is just like your car. You can use electricity and the gas, right? There's 3 models. Each model can be tweaked separately. And you can see the hybrid model, on the Tesla clean one, they can get 2.3. But testother, I think this guy, I think it's by Wang. He's very good. He managed to significantly reduce the hybrid models error compared to other hybrid models. I think this result is even better than lots of the end-to-end model because he's so good at tweaking models and design new networks. And the transformer means that the acoustic model is transformer. Okay. And the testother, they got 4.8. But this one doesn't work very well. Quasnet. I even don't remember who did the Quasnet. But the LAS system, okay. This is a standard transformer, okay. These are implemented by 2 different groups. And you can see this guy can do 2.2, fairly good. This guy can do this kind of weird to me because you can see that with the language model, they're doing worse. Yeah, they're doing worse. And then you can see they're not doing better than Dr. Wang, right? Dr. Yonghui Wang. Yeah, especially on testother. Testother is a kind of a noisy or data is kind of test data is distorted compared to the clean data. LSTM. I don't know what is LSTM. This is their implementation. So anything without a reference mark is their implementation. So if they implemented this, it seems that they're not doing better than Dr. Wang. But this is the transducer model. This is my guess, okay? Correct me if I were wrong. Okay, I won't stop guessing this, but let me take a look at the reference 7, okay? What is reference 7? Okay, I understand. So the transducer, they actually meant they use the RNT loss to train their in their decoder. So this is RNT. Where's my pen? They actually meant. Give my pen. They actually meant RNT loss. So what does the loss use? LAS use regarding their loss? They use CE loss. Okay. So LAS is not streaming. Okay. Not streaming, but the transducer model, although the encoder is not streaming wise, but you can, but they claim they're streaming, okay, or claim they're streaming. Okay, so this one, yes, indeed, I think that this paper, I read this paper before, is indeed it's not streaming because they use encoder. They took look at the whole sentence. It's not streaming. This guy did better than Dr. Wang regarding the hybrid model. Got 2.0, very good. ContextNet is a method which was published almost at the same time as the Conformer paper, okay? But ContextNet doesn't use CN. Correct me if I'm wrong. They try to model the context better in the transformer, just like the people they mentioned that during the introduction. They adopts the squeeze and excitation module in each residual block to capture longer context. So the context is longer, okay? This is why they call ContextNet. But, you know, the real speech guys do not like longer context. Why? Because it suggests that you cannot do streaming speech recognition, right? If you need longer text, then your model would have a longer delay to get a recognition result because you have to wait the context to be coming into your recognizer. And they use a conformer. I would say if you look at the text, first of all, when the numbers are close together, so I would first look at the WER without language model, because regarding the language model, with the language model in the LibriSpeech, they're using some external text which doesn't have audio corresponded to it. So the WER with language without the language model is the pure end-to-end model, pure end-to-end. So that means you just train a model which can be viewed as a acoustic model plus language model. And it's wrong to view that in that way, but it's a one unified model to do the acoustic and the language thing. Okay, but the WER with the language model is it's hybrid again. Okay, you see, you have your end-to-end model plus your external language model. Okay, it's hybrid again. So regarding the pure end-to-end, you can definitely see that their method in the clean case is as good as the context net, but they do better under the testother case. If you see they go from 4.6 to 4.3. This is almost like 5 to 10% improvement, which is significant, very, very significant. And when they are using the language model, although, you know, on the test clean case, they are still roughly the same, but they get about 5% improvement. This is 5 to 10 improvement. So at the time of publication, they have the state-of-the-art model, okay? So in terms of the ablation study, which is my favorite, I like to read the ablation study results. First of all, they want to see that for their conformer block, whether it's better than the transformer block. So they're trying to do this experiment here. So given the existing conformer blocks, they're removing one thing after another. Eventually they get the original transformer block, right? And during this type of this entanglement process, you can see how the performance drop after you remove one thing after another one, okay? And you can see, I would suggest just look at these two columns, especially this column, because if you look at test clean, you won't see much difference, okay, most of the time. And I think it's wrong to look at the dev clean, because dev clean, there's one thing you have to know, that for a LibriSpeech task, right now everybody start to use the dev set for tuning the model. So dev set is always kind of a overfitted scenario. So the training set, the dev set, the model is optimized on the dev set. So you can definitely see that the dev set means actually what's the best thing you can achieve on the set. Suppose you know everything, okay? Overfitted case. But a test case, so it's better to check the test other scenario. So the baseline is at 4.3. But if you replace the switch with the ReLU, I think what the author said is not here. Yeah, switch is better than ReLU for sure. See this? Get the degradation. And when you remove the convolutional block, you suffer the most. I think you suffer like 10%. This is like 10%. This is almost like around 5%, okay? Which is not bad. This is almost like 10%. And regarding the Macron FFN, I do not see much difference. This is like 2%, right? Not much difference. And also the relative position embedding. This is important, and this has been proved before. This is like another 10%. Okay. So my understanding is that this is the most important, and also this is also important, first level important. And this is the second level important. This may not be important. Okay. Oh. And also they tried to also do another ablation study of conformer attention. Okay. They replaced the depthwise convolution with lightweight convolution. So the lightweight convolution, in case you're interested, you can see this. So you can see it dropped like 10%. So literally speaking, although I haven't read the paper, it seems to me that this one has a less amount of parameter. Okay. So model size is smaller. They also try to do this a convolution block, change the order of this. So remember this one? So you have the convolutional module here, and the multi-head self-attention here. So what if you just move the multi-head attention after the convolutional module and move this forward? Just change the order, okay? The result is it only gets worse, slightly it's not slightly getting worse. It's no, it's getting worse slightly. It's less than 2%. So 2% is almost nothing. It might be a disturbance in your training, okay? But my personal favorite is to have a multi-hand attention before the convolution. That's my personal favorite. Why? I really can't tell why. That's my feeling, okay? Oh, sorry. I said it wrongly. My personal favorite is to have a convolution before multi-head attention. Because to me, my understanding is that convolutional stuff always works better for the raw signal. Okay, if you see the image or speech, people like to put a CNN layers at the bottom other than top. Okay, but in terms of attention, you see, remember in the transformer, not transformer, in the LAS, listen, attend, and spell model, the attention happens only after you finish the encoder, which is layers of LSTMs, okay, or CNs. So attention happens on top. Okay, attention stuff happens on top of a CNN. So this is interesting to see in this paper. They actually chose to put a multi-head attention before the convolution or at the bottom. But you also have to pay attention that this is just a one block. Okay, they have a one block on top of another one. So you have this convolution, attention, convolution, this type of thing, happening after another one. So it might not like the traditional or scenario where we are thinking about. Okay, and they talk about the parallel multi-head attention and convolution. I think this actually meant you have this attention here, attention 2, attention 3, attention 4, 1, 2, 3, 4, attention, and they for this they run a convolution. They run a 4 convolution here, and they combine these 4 things together. This one actually they give them about 10% increase in WR. It's not good. Regarding the Macron feed-forward module, I think the result is interesting. Although the author didn't give the reasons, let's look at the testother again, because I think you can only tell difference from here. This is like 5%. Yeah, both 5% reduction. So this is significant, definitely significant. First of all, you shouldn't use just one single FFN. Let's look at their picture again. So you say, wait, or the authors, can I just use just one feed-forward module, for example, I just have a toast, French toast. I don't like sandwich. I like a French toast. I don't want the things on top. Okay, suppose like you don't use this. So they also told you that you're gonna be suffering from this. You're gonna lose 5%. Okay, so you have to keep this. The second thing is that full step residuals. So if you look at Dr. He Kaiming's original ResNet paper, he uses the full step residual. But I think for speech, a lot of people use half step residual or 2/3 step residuals. So this is you see this one. Remember I talk about these things. Yeah, this is if you use a full step residual, this becomes 1. Why? I really don't know why. He also didn't explain. Number of heads. I think this is trivial. If you look at the number of heads, this is the best, right? Okay, these get worse, but not much. Most time you're less than 5%. So my guess is that LibriSpeech is not a big data set, so it doesn't matter. You don't need so many attention heads. Kernel size wise, I think nobody can explain this. It's convolutional kernel size. Nobody can explain this. Why it's the best thing is 32, right? Why is this? Nobody can explain this. Alrighty, I'm gonna stop here. Let me know if you have any questions or if I made any mistakes. Comment this and let me know.